Okay, uh, in this lecture, we'll discuss the minimization of finite automata. Minimization of finite automata means minimize the number of states. So, minimize uh, minimization minimization of finite automata means minimize the number of states. Number of states. And in this case, we have to merge those states which are equivalent. So merge those states which are equivalent. Which are equivalent. Now, how we define that the two states are equivalent? We can say that two states are equivalent. So two states, say q1 and q2, are equivalent if both of the transition function del q1 and x and del q2 of x are final states, or both of them are non-final states for all x string belongs to symbol belongs to sigma star. If they satisfy this, then we say that these two states are equivalent. Two states. Now, two states are k equivalent. We can say that two states are k equivalent. Two states q1 and q2. We can say that these two states q1 and q2 are k equivalent. K equivalent, where k is greater than or equal to 0 if both del q1x and del q2x are final states, or both non-final states for all string, that is x of length k or less. That means two states, that is q1 q2, we can say that these two states are k equivalent if both of these transition function with the string x of length k satisfy this condition. That means after both of these transition function on the string x are either final states or both non-final states, then we say that two states q1 q2 are k equivalent, where the length of the string is k or less. Now the relations that we have defined, that is the equivalence and the k equivalence, are equivalence relation. The relation that already we have defined are basically the equivalence, and the k equivalent are basically the equivalence relations. That means they are reflexive, symmetric, as well as the transitive. Now we do this while we try to minimize the finite automata. Every time we have to check this, and we partition those states are equivalent in a one subset. Means we partition, or the partition can be denoted as pi. So the partition can be denoted as pi. Partitions can be denoted by pi and pi of k. The element of this pi of k are k equivalent. Now if q1 and q2 are k equivalent, for all k greater than or equal to 0, then they are equivalent. Then they are equivalent. And if q1 and q2 are k plus 1 equivalent, they are k equivalent. If q1 and q2 are k plus 1 equivalent, then they are k equivalent. So these are the properties where the partitions can be denoted by pi as well as the pi k, and all the elements of this partition pi k are k equivalent. And if two states q1 q2 are k equivalent for all k greater than equal to 0, then they are equivalent. If q1 q2 are k plus 1 equivalent, obviously they are k equivalent. And last property, pi of n is equal to pi of n plus 1 for some n, where this pi of n denotes the set of equivalent classes under n equivalence, where pi of n denotes the set of equivalence classes under n equivalence. So these are basically the property that we have discussed here. Now the construction, how we can construct by using this concept. So there are few steps we have to follow to construct a minimum automata. So the steps are so steps 1, first we need to construct pi 0. So construct pi of 0. It means 0 equivalence. So 0 equivalence. What is this pi 0 equivalence? That is pi of 0 is basically it is a set where q1 0 and q2 0. We denote this pi of 0 is this. Where this q1 of 0 is basically is the set of all final states. And q2 0 is basically defined as q set difference q minus q1 0 is basically set of non-final state. It basically is the set of all non-final final states. So this is the step 1. First we have to distinguish two subsets. In one subset contains all the final states and another subset contains all the non-final states. Now step 2. And in step 2 we have to construct pi of k plus 1 from pi of k. That means from k equivalent classes to k plus 1 equivalent classes we have to construct. Now to construct this we assume let qi k be any subset of pi k, we assume that this is a k equivalence and qi is be the any subset of pi k. If q1 and q2 are in qik, means two states q1 and q2 belongs to this subset qik. They are k plus 1 equivalent, provided del q1 comma a and del q2 comma a are k equivalent. Means after transition delta q1a, delta q2a, a is a symbol, input symbol. If they are k equivalent, then we say that they are also in k plus 1 equivalent. So basically, what is the meaning of this? Meaning is we have to find out whether, whether del q1a and del q2a are in the same equivalent classes same equivalent classes in pi of k, that means k equivalence, for every a belongs to the input symbol. If so, that means if they satisfy this property, that means by taking input a for both of these state q1 and q2 are in the same equivalent class in the k equivalent or pi k for every input a, then we can say that these two states are also in k plus 1 equivalent. If so, then we can say that q1 q2 are k plus 1 equivalent. If so, then we can say q1 and q2 are k plus 1 equivalent. So in this way, qi of k further divided into k plus 1 equivalent classes. So in this way, qik be further divided into k plus 1 equivalence classes. And we have to repeat this procedure, step 2, we have to repeat. And for every qik, and we have to repeat this procedure for every qik. We have to repeat for every qik in pi k. That means kth equivalent classes, we have to check all the subset and we have to repeat this procedure. Clear? In pi, those are in pi k, to get all elements of pi k plus 1. We have to obtain this pi k plus 1. Now step 3. Now construct pi of n for n equal to 1, 2, up to until for some value of n, pi of n is equal to pi of n plus 1. Then we have to stop. Now we'll give an example based on this concept, then it will be more clear for all of you. We assume that a transition table is given. Example, suppose we have given a transition table like this. Suppose state and this inputs are 0, 1 and states are q0, q1, q2, q3, q4, q5, q6 and q7. Right? And this is a initial state and q2 is the final state. Now by taking from q0, it will be q1, then q6, q0, q2, Q7, Q2, Q6 and Q6. And by taking 1, these are the states 5, Q2, Q2, Q6, Q5, Q6, Q4 and Q2. So what is the first step to minimize this automata? First step was we had to construct pi of 0, right? So we have to construct pi of 0. So what is pi of 0? Pi of 0 is basically this q1 of 0 comma q2 of 0. What is q1 0? Q1 0 is a set of final states and q2 0 is a set of non-final states. So from this transition table there is a single final state, that is q2. So we can write that is q2 corresponding to q1 0, and q2 0 is basically all the other non-final states. So except q2 all states will be there: q0, q1, q3, q4, q5, q6 and q7, right? Now from this, so this is a pi of naught. Now from this we have to construct pi of 1. As we have mentioned that we have to construct, that is from pi of k we have to construct pi of k plus 1. So in this case pi of 1 will be constructed from pi naught. Clear? So now how we construct this pi of 1? So we have to take subset, all the subsets of pi naught we have to take, but in this case it is a singleton set, that is q naught, q2. So we just look into the other set, that is from q naught, q1, q3, q4, q5, q6 and q7, and check whether they are k plus 1 equivalent or not. Now first take q naught and q1. So for every symbol, here the symbols are, here the symbols is basically 0, 1, 1. So for every symbol 0 and 1, either they belongs to, after transition, either they belongs to the final state or they belongs to non-final states. That means they belongs to in the same equivalent class of pi 0. Now we'll check each and every one. So let's see. Suppose you are in q naught and q1, whether they are uh, k plus 1 equivalent or not. So now del q naught 0 and del q1 0. What are the next state? In case of q naught 0, it is q1, and q1 0, it is a q6. That means both of these q1 and q6 are non-final states, right? And obviously look into this, they belongs to the same equivalent classes because this is one of the classes. So q1 and q6, q1 and q6, this q1 q6 belong to the same class. Now we have to look for 1. Now for 1, what are the outcomes? If the input is 1, so it will give you output q5, and for q1 1, it will give you the output q2. Now q5 belongs to this equivalent classes, but q2 belongs to another classes. So they are not zero equivalence. Clear? So they are not in the same equivalent classes. So they are not k plus 1 equivalent. That means Q0, Q0 and Q1 are will not be in the same set of pi 1. So what we can write? We can write that is Q2 will remain same, but here just Q0, Q1 will not be in the same classes. Now we have to check Q3. Now look, if it is Q3, so now in case of Q3, if we assume that it is a Q3, now Q3, Q3, and if your input is 0, Q3 input is 0, so that is Q2. Look, for 0 it will be Q2. Again, it is Q1 and it is Q2. Like, so Q0, Q1 is on equivalent classes, but Q3 outcome Q2 is another equivalent classes, another class. So Q3 also not go in the same set of or same equivalent classes of with Q0. That is, now we have to check. So Q4. Now for Q4, now Q4, if we take 0, Q4, so it will be Q7. Now it will be Q7, right? So Q1, Q7 are in the same equivalent classes, Q1 and Q7, no problem. Now if we take input 1, so it is Q5 and Q4 1, Q4 1, it will give you the Q5. So obviously Q5 in the same equivalent classes. So Q0 and Q4 will be in the same classes of pi 1. So Q4 will go into the same set, same subset, Q4. Now we have to check Q5. Look, Q0 and Q5. Q5 again there is a set Q2 which is in another class. So Q5 also will not come with this set Q0 and Q4. Now we have to check Q6. Q6, in case of Q6, Q6, if we take Q6 0, then it will give you the Q6. So Q1, Q6 are in the same equivalent class. And if we take 1 from Q6, it will go give Q4, Q4 and Q5 are also in the same equivalent class. So Q6 also come with the same subset, right? Now we check Q7, and in case of Q7, if we take 0, so it will give Q6. So for input 0, there will be no problem. Q1 and Q6 will be in the are actually in the same equivalent classes. But for 1, Q0 gives 5, but from Q7, by taking 1, you are in the Q2 state, and Q2 is another equivalent class. So Q7 will not go into this set. So now we have completed this procedure here. Now we have to check the remaining states in this same equivalent classes. So what are the remaining states? Q1, Q3, Q1, Q3 and Q5 and Q7. Now we check whether these are pi on equivalence or not. Now first we check Q1, Q1 0, and then we check with Q3 0. Q1 0 obviously gives Q6 and Q3 0 gives Q2. Look, so Q1, Q2 and Q6, Q6 belongs to the same equivalent class, but Q2 belongs to other. So Q3 will not go into the same subset with Q1. So now Q1. Now we check Q5. Now we check Q5. So by taking Q5, obviously again the same problem occurs. Q5 outweigh Q2. So now Q6 is in the same equivalent classes, but Q2 is another. So Q5 also not go into the same subset with Q1. Now we check Q7. Now we check Q7. So now Q7, by taking 0, it will give you Q6. So Q6 in the same equivalent classes of pi naught. And by taking 1 Q1, it will give you the Q2, and Q7, it will also give the Q2. Look, by taking 1, they are in the same Q2, both are in the same equivalent classes of pi naught. Similarly, Q6, Q6 are also in the same equivalent classes of pi naught. So that means Q7 can go in the subset with Q1. So that means Q1 and Q7 are in the same equivalent class of pi 1. Now remaining states, again we have to check the remaining states, that is remain Q3 and Q5. Now we have to check Q3 and Q5. So del Q3 and del Q5 by taking 0. So Q3 0 gives you the Q2 and Q5 0 gives you Q2. So no problem in this scenario because both of the states are basically in the same equivalent class in pi naught. Now take 1. So Q3 1, Q3 1 give you the Q6 and Q5 1, Q5 1 gives you the Q6. So Q6, both of the states are in the same equivalent class of pi naught. So Q3 and Q5 belongs to the same equivalent classes in pi 1. So all the state, uh, uh, all the states we have covered in pi 1. Now we further check for pi of 2. That means we have to check whether they are 2 equivalent, pi of 2. That means whether they are k plus 1 equivalent, and we have to construct pi of 2 from pi 1. Now again Q2 will remain same. In this set we have to check every subset, we have to check of pi 1. From pi 1 every subset. So this is one subset, this is another, this is, and this is, we have to check all. Now first we check Q0 and Q4. Q0 and Q4. 0 0. Now Q0 0 gives you Q1 and Q4 0 gives you Q7. Look, Q1 and Q7 belongs to the same equivalent classes of pi 1, right? This is the same equivalent class of pi 1, so no problem. Now if we take 1, so Q0 gives you, by taking 1 it will be Q5, and Q4 1 gives you the Q5. Obviously Q5 belongs to the same equivalent classes of pi 1. So Q0 and Q4 will go into the same equivalent class of pi 2. So now Q0 and Q4 will be in the same subset. Now we check Q0 with Q6. Q6. So now it is a Q6. Now taking 0 Q6, it will be Q6. Look, Q1 belongs to this equivalent class, but Q6 belongs to this equivalence class. So they are not in the same equivalent classes of pi 1. That's why q1 q6 cannot go with the subset where q0 and q4 belongs. That means q0 and q6 are not pi 2 equivalents. So this will complete and q6 will remain in a singleton set. Now we have to check q1 q7. Obviously, by looking into this transition table, we can do this. Q1, by taking 0, it gives Q6, and Q7 by taking 0 gives Q6. So Q6 belongs to the same equivalent classes of pi 1. No problem. Now by taking 1 from Q1, by taking 1, it will give you the Q2 state, and Q7 it will give you the Q2 state. Obviously Q3 are also in the same equivalent classes of pi 1. So there will be no problem for Q1, Q7. They are in the same equivalent class of pi 2. Now we check whether Q3 and Q5. Again we check. Q3 gives Q2 by taking 0, and Q5 gives Q2. So Q2 belongs to the same equivalent class of pi 1. So no problem. And for 1, Q3 1 gives Q6. Q5 1 gives Q6. So again they are in the same equivalent classes of pi 1. So Q6, Q3 and Q5 are in the same equivalent classes of pi 2. Right? Now, if we further partition, so that means now we have obtained pi 2 equivalent classes and we have to further proceed. Now, uh, we have to construct pi 3. We have to construct pi 3. From where? From pi 2. So obviously Q2 will remain same. Now we have to check Q0, Q4 will be in the same equivalent classes of pi 3. Go. Now check. Q0 by taking 0 it will give Q1 and Q4 gives Q7. So Q1, Q7 are in the same equivalent classes of pi 2. So no problem for the input 0. And Q0, Q4 by taking 1 it is Q5 and Q4 gives Q5 obviously are also in the same equivalent classes of pi 2. So Q0 and Q4 are in the same equivalent classes of pi 3. So it will be Q0 and Q4 will remain same, and Q6 is a singleton set, no problem. And now we'll check Q1. Q1 gives Q6 and Q7 gives Q6. They are in the same equivalent classes of pi 2, right? Q6 and Q1 by taking 1 Q2, Q7, Q2, they are also in the same equivalent classes of pi 2. So there will be no problem for Q1 and Q1 and Q7. Now we check Q3 and Q5. Q3 by taking 0 gives Q2 and Q5 also gives Q2. Q2 belongs to same equivalent classes of pi 2, no problem. And Q3 by taking 1 it gives Q6 and Q5 gives Q6. So Q6 also belongs to the same equivalent class of pi 2. So there will be no problem. So they belongs to Q3 and Q5 belongs to the same equivalent classes of pi 3. Now look into this pi 3 and pi 2. Right? Pi 3 and pi 2 are same. Now we have to stop. So that is pi of 3 is basically pi of 2. That is no further partition is possible. Now we have obtained the minimum number of states automata. So we can write the minimum state automata m dash, it is a minimize, where it is a q dash. That means after minimization the number of states actually reduce, and the input symbol is 0 or 1, and delta transition function will be changed, initial states also will be changed, and final states also will be changed, where this q dash set of states are basically, look, q2, then q naught, q4, then q6, then q1, q7, and then q3 and q5. And initial state will be this q0, q4, and final state will be, sorry, and final state will be f dash, it will be q2. Now what will be the transition table for this minimized automata? That means we have to define the delta. So now delta dash is defined as, we can write state and sigma, that is that is 0 1. So initial state is q naught and q4, right? Then by taking 0 from q naught, that means by taking your initial state is q naught q4, and in this transition diagram q naught q4, it will give q1 q7 by taking 0, and by taking 1 it will go q5, right? So we can write q3 q5, and q5 means what is the state that is associated with q5. So we can write it will be q1 q7, and it will be q3 and q5. Now q1 q7, from by taking q1 and q7, right, it will go q6 and it will go q2. So obviously it will be q6 and it will be q2. Now q2, so from q2 q naught, and by taking 1 it will be q2. So now q naught is not a single, because after partition q naught basically and q4 are equivalent. So that's why it will, this state will be q naught q4. So now it will be q naught and q4, and it will be q2. Now q3 q5, and q3 q5, by taking q3 and q5 it will basically go to q2 and q6, and q6 is not a singleton set because okay, q6 is singleton set, no problem. So now it will go to q2 and it will go q6. Now last state, where is the q6? Now q6 by taking 0 it will go to, by taking 0 q6, by taking 1 it will go to q4, but q4 is a not singleton state, because Q0 and Q4 are equivalent. So that's why Q0 and Q4 will be the state. So it will be from Q6 by taking 0, it will be in Q6, but here it will be Q0 and Q4. So this is the transition table for the minimized DFA. Now we can draw the transition diagram like this. Oh, here it will be Q0, Q4 is one of the state, Q2 will be another state, Q1, Q7 will be another state, Q3, now Q3, Q5 will be another state, and Q6 will be the another state. So these are basically the states. We mark this states. Clear? Now what is the final state? Obviously we know Q2 is the final state. Right? Go here. Q2 is the final state. So we mark it as a final state. And it is income initial state Q0. Now from Q0, Q4 by taking 0 goes to Q1, Q7, and by taking 1 it goes to Q3, Q5. Now Q1, Q7 by taking 0 it goes to Q6, and by taking 1 it goes to Q2. Now Q2, from Q2 by taking 0 it goes to Q0, Q4, and by taking 1 it will remain in the same state. Now go to Q3, Q5. Q3, Q5 by taking 0 it goes to Q2. So we can write in that way 0, and by 1 it will go to Q6, and Q6 by taking 0 self below, but by taking 1 it will go Q0, goes to Q0, Q6. So this is corresponding the mini transition diagram, and it is a transition table of minimized automata. So number of states here is a 1, 2, 3, 4, 5, but initially it was a total 8 number of states. So after minimization, we have obtained only the 5 states. So this is the basically procedure to construct a minimum state automata. And what is the procedure in summary? First, we have to zero equivalence. We have to find the zero equivalent classes. So which is denoted as pi of naught. And here basically two subset will be constructed. One is the set of final state, another is the set of non-final states. And then there will be construction. Repeat this procedure. We have to construct pi 1 from pi naught by taking whether they are in the same equivalent classes, by taking all the inputs. If so, then they will be in the same equivalent class of k plus 1. That means after taking the string or symbols uh, for any two states of a particular subset, if they are in the same equivalent classes of k, then if they satisfy this condition, then they will be in the same equivalent classes of k plus 1. So this procedure will be repeated, and after some times we'll see that no further partition will be possible, and we have to stop, and then the number of states at that time is basically the minimum number of states. So thank you.